So yeah, I'm Adonis. I'm here to talk to you about extracting linguistic information from text. And the agenda for today, other than introduction and the problem definition, we're going to talk a little bit about extracting morphosyntactic agreement rules and then doing cool stuff with them. Then we're going to talk about discovering semantic subdivisions and then using them in cool applications, or at least what I think are cool applications. And then we're going to talk a little about, very briefly, about potential future work. So yeah, about me, as Emily said in the introduction, I'm an assistant professor at George Mason University. I work in NLP in general, and my goal is to build NLP that works for everyone. And that means basically, that I have several different projects that involve they involve NLP for dialects, which are largely ignored in modern NLP literature, NLP for L2 speakers. So for example, I'm a non-native English speaker, and that means that my English is slightly different than a native speaker's. So I want Google to understand me just as well as it understands my wife. And other stuff like NLP for documentation of endangered languages, which I think is a really, really important problem, and that's what I did my PhD on. And then other important side issues like cross-lingual fairness and things like that. So that's not what I'm going to talk about, although what I'm going to talk about is related to the documentation of endangered languages to an extent. But if you want to talk about it, just reach out to me, or we can talk if you have any questions at the end of the talk. I'll be very happy to talk about some other works. So let's go straight to the general problem definition. So let's start with, why do we even need language descriptions, and why do linguists spend so much time creating them, right? The answer is very simple. Languages are complex, and understanding them gives us a lot of understanding into how humans encode knowledge, potentially into our brains and stuff like that. So, I mean, I don't think there's any question as to why we need it. But let's look at very simple examples, right? So we have, let's say, English, and you have a very simple sentence, that boy is eating. And in English, you can very easily take boy out, put in girl, and there's nothing else you need to change, right? English is kind of boring. Then let's take that sentence and let's see how that sentence looks in Marathi. Okay, I don't speak Marathi, but my student Aditi told me that this is pronounced to mulga gefto ahi. And you'll already notice some differences with English. The auxiliary and the main verb are swapped in their order. And then there's the determiner to and the noun mulga, that really just means, basically, if I were to gloss this sentence, you would read that boy eating is. Okay, so now in Marathi, you cannot do that thing that we did in English, where we're going to substitute the word for boy, mulga, with the word for girl, which is mulgi, and get a grammatical sentence. And the reason for that is that in Marathi, the noun needs to agree with the determiner. So you need to say ti mulgi, and also with the verb. So you need to say ti mulgi gevte, as opposed to to mulga gevto, which is what you'd say for the boy, right? So there's a lot of linguistic phenomena that are governed by rules, and these rules are described in syntax, in morphosyntax, and these rules can also be depending on the semantics of the words, and so on. So what we're trying to do is uncover these type of rules by just looking at text, like a bunch of raw text in the language. And in a way, it kind of feels like that's exactly what linguists do, right? So if you think of a linguist who's not a native speaker of a language and goes to analyze another language that they don't know, then they will collect a bunch of data, and they will sit down and analyze them. Obviously, they're also doing this in conjunction with native speakers, so they can ask them questions, they can get feedback on why do you say this that way and not that way, and so on. But we don't have that. What we're going to do is try to get at least some type of linguistic rules derived straight from raw text. So for example, here we would like to know, to learn that in Marathi, the determiners that modify a noun, they need to agree with that noun with respect to their gender. Does that make sense? So I don't think there will be any questions here, so I'll just go ahead. If there are, interrupt me or write it in the chat. So let's look first at extracting agreement rules, morphosyntactic agreement rules. So what is morphosyntactic agreement? So basically, it's the phenomenon where one word will select its morphemes, so it will have a specific form in correspondence with another word in the sentence. All right. This can happen for different grammar categories of types of morphemes, for gender, for person, for number, and it's pretty common in many, many languages. I don't know if there's any language except for maybe some isolating ones that don't have some sort of agreement. But there's a crucial point here that if we have a bunch of data, there's going to be a lot of agreements throughout the sentences, but not all of them are governed by a rule. So let me show you an example. So let's say we have this Spanish sentence, mi hermano tiene un perro. Okay, that means my brother has a dog. And the order of the words is exactly the same as in English. And you'll see that hermano, tiene, un, and perro are all in the singular number. Okay, so there are multiple agreements, but let's look just now in the agreements between the verb, tiene, to its subject, the hermano, and to its object, perro. Okay, now all of them are agreeing, everything is in singular number, but only one of them is because of a rule. So in Spanish, you can also say, mi hermano tiene muchos perros. So my brother has many dogs, right? So now this is another grammatical Spanish sentence where the subject still agrees with the verb, but the object does not. So ideally, we will want to learn that subject-verb agreement is required in Spanish. And we will also want to learn that object-verb agreement in terms of, of number is not required. Or what we call, I'll call in the next slides, chance agreement, right? Because we observed it in general, chance over a big corpus. So the way that we're going to do this is we're going to devise this little task where given two words and the dependency link between them and their part of speech tags, we are going to try to predict whether these two words that are already linked by a dependency link should agree or they should not. Yeah, so if you get these, let's say what we're going to do is over the training data, we're going to have raw text. And first, we're going to parse it. And we're going to use the dependencies for the universal dependencies formalism, just because it's one, as far as I know, of the few ones that can actually scale to many, many languages. And that means we can use it, on about 100 languages to test our models. With a caveat that we're not actually using the real universal dependencies, we're using syntactic universal dependencies that have some, basically, that follow what linguists know are basically proper syntax. So now we have this sentence. We have the links between the words. We also have the part of speech tags corresponding to each word, and we also have a morphological analysis, right? In practice, we are doing this over the universal dependencies data, but we also used parsers to parse a larger raw corpora. Okay, so now for each of those links, we're going to look at the part of speech tags and focusing on a specific grammatical feature. We're going to have a label that tells us whether the two words across those this link agree. So for example, here, there's in that box, there's a determiner link between the determiner and a proper noun, the second and the third word. And so what we're going to do is we're going to create a training instance where we're going to have a proper noun linked through a determiner to a determiner, link to a determiner word, and then these two agree in terms of their gender, right? So agree, the label will be yes, they agree. We're also gonna have, let's see, for example, here, we're gonna have now a link between the first and the third word, where it's a noun and a proper noun connected through a modifier link, and these do not agree in terms of their gender. The first one is neutral, the second one is feminine, and so on. So basically, we decompose the whole tree into just pairs of words linked, and now the label that we are going to try to predict is whether these words agree in terms of their feature that we care about. In this example here, gender. Yes, Nathan.
So a clarification, are you, the task formulation is to predict agreement at the token level, right? And not
at the pair of tokens level, yeah.
Okay, so it's not in general should the subject relation have agreement, or do you also look at that?
We're gonna train a model at the little word level, and then we're gonna use that model to extract general rules.
Okay, good.
Yeah. So so here we have created now this training data at the token level, essentially looking essentially at the dependency link level, and what we do is we're going to train a model on this training data. Okay, and our model is going to be a simple decision tree that receives, in each case, these three features: the part of speech tag of the first word, the part of speech tag of the second word, and the type of the dependency link that connects them. And it's going to try to predict whether these two words should agree or not. So we have our dependency, or we have our decision tree that we've learned over these training data. And now what we're going to do is we're going to use this dependency tree and to extract rules at the general level. So here's what this looks like. So let's say for Spanish, we have created this training data over a big Spanish corpus, looking at just the gender feature, and we learn that model, and this is what the model looks like. It gives us a very small dependency tree that says, hey, if the part of speech tag of the child in the link is either an auxiliary verb or an adjective or a verb or a pronoun, then and the relation is any relation, or the head part of speech tag is any, then there's like very large agreement. So the decision tree would predict, yes, these things should agree. And then there's these other leaves, 1 and 2, where the output would be agree for leaf 1 and agree for the leaf 2, right? So in this very simple dumb decision tree, which basically in every leaf would predict that this is, the output should agree. Okay. Now, the interesting thing here is that in each leaf, if you look at the amount of examples that is essentially the support for that leaf, some of them actually agree and some of them do not agree. Here, that means that, each of these little links. But then these different distributions look very, very different, right? So in leaf 3, there's way more examples that agree as opposed to those that do not agree. Whereas in leaf 2, at the bottom right, the amount of examples that agree or do not agree are more or less the same, right? There's 260 to 370. So what we're going to do is we're going to now take each leaf and we're going to decide on whether that leaf basically corresponds to a required agreement setting, which means that we could potentially extract a rule from that leaf, or if it corresponds to a chance agreement setting. So what we do is we take each leaf and then we do a little bit of statistics on it. So a simple idea would be, well, if to apply a simple statistical threshold, if more than 95% of the examples that are in the support of that leaf are actually agreeing, say that it is probably a rule. Okay, this is not what we're doing. This is like a simple like idea. What we're actually doing is we're using significance tests, the chi-square significance test, to make sure that the observed distribution actually is significant compared the difference of the observed distribution is significantly different than a random one. And we also want to make sure that the effect size, basically the amount of examples that we have in our leaf, are enough to support our argument. Okay, so we do this thing, and then if both of these tests pass, then we say, yes, this is a required agreement. Otherwise, we're going to say, yeah, all of the links that fall under this leaf, they probably agree because of chance. So following these, applying to the previous tree that I showed you, the same, the statistical tests that I told you about, basically allows us to label leaf 3 as required agreement, and leaf 1 and 2 come back as chance agreement, right? So they don't pass the statistical tests. Now, this is not very interesting. Basically, this is saying that for every link where the part of speech tag of the child is any of a determiner, a pronoun, a verb, or a proper noun, or an adjective, then it should agree, right? So there's some in here that we know that are correct because it's Spanish, such as, the determiners and nouns need to agree, or the adjectival modifiers of a noun need to agree with a noun. But, there's other, a little bit of junk in this leaf. So our actual trees are bigger than this. So we allow them to be much bigger and more fine-grained. I'm just showing you this kind of like coarse tree because it's, it fits my slides. Okay, so now basically what we did then is show those rules to linguists and ask them to evaluate them. So we had this model prediction, where by model I mean not the decision tree, but our model that looks at the decision tree and extracts a rule. And then our model said that a verb and a pronoun that are connected through a subject link, they have required agreement. So what we do is we take the rule, we find examples in the tree banks that follow that rule, and we also find examples, if there are any, which usually there are, in the tree banks, where we have a verb and a pronoun linked through a subject that do not agree in terms of, say, number, as is this example here. Okay, so we show them like 10 examples that follow the rule or follow what our model thinks is a rule, and then as many examples as we can find where the examples seem to not follow what our model thinks is a rule. So we show them to these, and so the humans can look at all these examples, and then they can tell us if, oh yeah, this is actually a rule, which means that yes, two things that look like that, like a pronoun and a verb, almost always should agree, or they don't need to agree, which corresponds to our chance agreement label, right? And then we just compare our model's predictions with the labels that the humans give in each rule. And in doing so, which I will show you the results later, but beyond just the evaluation with the humans, which doing a scale is really hard, Kat, who is here, actually did the Russian one and gave us a ton of feedback on how hard this is and how painstakingly, how much time does it take to just look at all of the examples for a single rule. So, we want to do this at scale over all of the possible rules that our model thought could be actual rules or, chance agreement rules. So what we can do instead is we can also look at how well our decision tree does, how well our process does on unseen data, right? So if we have unseen data and we also have parses for them, then we can compare how many times the things that we say are rules are actually validated, okay? So again, we are going to have our models predictions over test data, where if something is a rule, we will always say that yes, they should agree. Or if it's chance agreement, we're not going to say anything. And then we're going to look at what happens in the actual distribution on the test data. So basically, if our model says that something is a rule, we're going to have a 1% or like 100%, sorry, expectation that all of the examples agree. If the empirical distribution says that 97% of the examples actually agree, then our rule was correct, because it's, well, not correct. We measure the distance essentially between those two things, right? Well, we say it should be 100%. The empirical distribution is 97%. There's a 3% distance. If it wasn't really a rule, the assumption is that the empirical distribution is going to be closer to chance. So the empirical distribution is not going to be like 97% agreeing examples, but they're going to be maybe, I don't know, like 60% or 50% if we have a ton of data, right? Great. So that's how we can evaluate our model also automatically. So let me just show you some results where here we're working with actually gold standard syntactic analysis from UD, which has errors, but let's ignore that for now. We can measure the accuracy of our rules compared to the ones that we find in the test data, the empirical distributions. And basically, the finding is that in the languages that do have agreement, like Baltic languages, Slavic languages, and Indo-Aryan languages, all of these we can actually do really well at making these predictions and identifying which pairs should actually agree. Here, the comparison at 0 is assuming a baseline of chance agreement, right? Assuming that every agreement we observe is by chance. And you'll notice that in some cases we do a little worse. So in Uralic languages, we do worse than chance for predicting agreement for persons. But for most of them, we actually do better than chance. And now basically that's like the first summary of this work, that our framework extracts decent first pass rules under gold standard analysis. Note here two things: decent, I'm not claiming that I'm able to create a grammar, and two, the second part is under gold standard analysis, right? So here we have gold parsed data. Comparing to the annotations that we got for Russian from Kat and from some other linguists for Greek and Catalan, in total we had them evaluate about 120 rules, and then we compute the correlation of what our model says to what the humans say. Across all of the different features, there is some moderate correlation. But if we look at some of them, like gender and number, which all of these languages, both Greek, Russian, and Catalan, are required agreement for many, many cases, then we have much higher correlation. So the next question is, now what happens if there's no gold standard syntactic analysis, right? So I told you that linguists do this on endangered languages and on new languages that maybe they are not familiar with. So what we did to simulate that scenario is work with simulated low resource data, where we took the standard analysis, and instead of using all of them at the gold level, we took a small chunk of it and keep it gold, and then the rest of it was the output of a parser thing. It was like UDify, and yes, UDify. And we did a little bit of tinkering to make sure that the parser works well for the language that or as well as we can for the language that we study in each case. And then we aggregate these now noisy parses and then run that whole thing through our process, right? Learning the decision tree and extracting rules and so on. So the results here show how we did on extracting rules for Belarusian. depending on how many gold examples we gave to the parser, to our framework. And you can see some interesting things where if we don't do cross-lingual transfer, where we initialize the parser with Russian, basically we do terrible in a zero-shot setting. But if we do initialize the parser, we can do very well. Like we can extract rules with more than 50% accuracy when we have an informed parser, even in a zero-shot setting. And then when we add more data, we get a little better. So basically, using transfer learning for your parsers can actually help create meaningful trees, and that still makes us allows us to extract decent first parse rules, even in a zero-shot setting. And then we also did some true zero-shot settings in looking at tree banks that don't have a training tree bank, at languages that don't have a training tree bank on UD. So these are languages like Tagalog and Faroese and Welsh. And well, we find that basically here we're comparing our accuracy against the random chance baseline. And you can see, for example, that we were able to identify that, yes, there's some rules here. All of these are aggregates over different rules, but there's some rules that we can uncover in Welsh for gender, and some rules that we can uncover for number in Faroese and so on. Yeah, so that's what I have in this section. Any questions? I know I run a little bit. Yeah, Nathan.
This is cool. So one question is SUD, does SUD always ensure that agreement is local to an edge if the parse is correct? I know this should be the case for, languages that I've studied, which tend to have, function word, where function words are heads in terms of agreement. But
yeah, so I think the answer is no. And I'll give you an example that's similar to the one that I started with, right? So in Marathi, when you have auxiliary verbs and then a main verb, it's the main verb that needs to agree with the subject.
Right.
Whereas in the European language like English, it's the auxiliary, right? So if you use standard UD, you're already doing great in Marathi because you have the link that you need. But if you use SUD, then you're losing that link. And it's the opposite, for example, in Spanish. So there's little things like that. We went with SUD, frankly, because most languages, I feel like, I don't know, at least most of the languages in UD are Indo-European, I guess. But in theory, there's nothing stopping you from trying the same thing on, standard UD versus syntactic UD and trying to extract rules from both of them or something like that. Yeah, but I like that question. Maybe we should have done Marathi with a standard UD now that I think about it. Although we didn't evaluate Marathi, I think. It's really tiny tree bank.
Any other questions? You can just use your microphone.
All right, well, I'll go ahead.
I have a question to you. So I wasn't sure I got it very clearly. So when you have agreement that say depends on the tense, like for instance in Russian, in verbs you have in present tense one set of categories that would agree. In the past tense you have other. For instance, you have like gender. So how do you deal with that?
We don't. That's why you'll see that our scores in Russian are a little lower, and especially also on the correlations here are a little lower than for Russian than they are for Greek and Catalan. I think because of that, at least for number. Is that correct?
Yes, I think.
Yeah. So so we currently don't use any other features. in theory, you could just add these other features as features on your decision tree, because you have them, right? So you could have, we could have had, rather than just the part of speech tags and the entity link, we could also have a feature that gives us, I don't know, the tense, as you said in Russian, the tense of if it exists, and if it does, like what value does it have? And then try to learn it. We did something like very simplistic, that, you know, as a first step to see if it's even feasible to extract rule like that. We are actively working on making it, you know, like a more informed model that can extract more fine-grained rules.
And where do you get the initial set of the potential categories that would agree? Like, for instance, like gender. So you just take all the set, like.
Yeah.
And,
I mean,
and
really,
the combinations, or just individual categories? If something agrees in gender and number, for instance, or something like.
They're not in combination, they're just by itself. So we have a different model for each of those categories. And, you know, we worked on them because, okay, like we know how the, you know, the powers that be decided that we should analyze languages. And these are the categories that we know that tend to, or at least there's some sort of agreement across the world languages, and then we focus just on those. We didn't do anything beyond that.
Okay, thank you.
Sure. Yeah, Emily.
Yeah, actually, so this slide reminds me of the question that I had was, do you think that with the scores being different, that this says something about like typology, how transparent or regular that morphologies are?
I mean, maybe. I mean, in theory, I'm trying to think. A rule, I'm trying to think of how our rules might relate to entries, say, in the WALS database, right? Which, okay, in practice, we know, or if you don't know, I'm telling you that there's no language where you can be like, okay, yes, the subject is always going to be before the verb or something, or agree with the verb, right? So there's going to be like a 97% or a 90% or a 61% over if you actually look at a big corpus. I mean, you can probably say things about typology. I haven't thought about that.
No problem. That's kind of a broader question. Thank you.
Cool. All right. So yeah, then let me go ahead and show you, now that we have these rules, what we can do with them. And what we did, at least, there's other things that you could do, like tie them to typology, Emily. We decided to use them to evaluate automatic language generation. So the idea is we want to create a linguistically grounded evaluation of the well-formedness. And the thing that we particularly care about is multilingual settings. Grammatical well-formedness, what is it? It's basically the thing that says that this German sentence here in the left sounds weird to a German native speaker, okay? If you say, ich werden lange Bücher lesen, then the auxiliary verb werden doesn't agree in number with the subject, and, you know, a native speaker will complain. Okay, there's also other types of well-formedness. There's also case agreement. So if the adjective here, langen, was in dative case, but the noun that it modifies is in accusative, again, a native speaker will complain if they hear that N. And there's also, for example, case assignment, right? So if you instead said, mich werde lange Bücher lesen, then now suddenly the subject is in accusative, and again, that's not something that German speakers like. They want their subjects to be in the nominative case. Okay, so this is the type of thing that we want to make sure that, you know, language generation systems like chatbots, machine translation systems, summarization systems, whatever, you know, actually adhere to those grammatical rules. And we want a way to evaluate the well-formedness of the text that they generate. Notice that well-formedness is different than fluency. Okay, well-formedness is necessary for fluency, but is not sufficient. But it's easier to focus on well-formedness because we can just compute, like have a checklist of rules that we want our outputs to satisfy, so we can easily measure. And as I showed you before, such rules can be extracted automatically and fairly accurately. So this is basically this rehashing the same thing from before, although we did extend this work, so it doesn't only cover agreement rules, but we also cover case assignment rules. So saying that a specific word that is linked through a dependency link to another word should be a specific case. So it should be in nominative or in accusative or in dative or whatever. And also the verb form choice rules. Cool. So again, the rules, the way that we extract rules are essentially exactly as before. For agreement is the same thing, except here abstracted away and say that we have a threshold. We don't, we still do proper statistical tests. And then when we have that, we have a rule that says, for example, if we have an adjective modifying a noun in this language, these two things need to agree in gender. Okay. For case assignment, the idea behind it is that if you look at the distribution of cases on the corpus in general, right? In this example, I think it's German, like, and you look at all of the things that, all of the nouns that, you know, always have case in German, and some of them are 30% of them. If you look at the blue bars, 30% of them are in nominative, 11% of them are in genitive, 25% are in accusative, and 33% of them are in dative, right? This is throughout the whole corpus without looking at anything else. Now, if you only look at the nouns that are the object of a verb, right? So you localize now your counts over only the nouns that are linked through a verb to a verb through an object dependency link. Suddenly that distribution changes and it becomes that green distribution here. So suddenly 86% of these nouns are in accusative, whereas only 10% of them are in nominative, and there's basically no dative and genitives in there. So now we do again proper statistical tests, and we say from there we extract a rule that says, hey, objects in German should be in accusative, for example. Or they shouldn't be in genitive or dative, right? Because that's not what we observe. Cool. So we have again the same rules. We run the same setting of evaluation like we did before. Like that, you know, they should almost always actually it's a true rule, or it need not be true. And long story short, we did this for Greek and Russian and Italian this time. And in most cases, at least for Greek and Italian, our rules are actually pretty decent. Most, you know, the linguist said, yes, these are actually rules. So you can put them in your checklist. So now that we have our checklist, basically that's we're gonna use and create this metric called LAMBRA, linguistically aware morphosyntax-based rule evaluation. And the nice thing about this is having this like checklist of rules that we're gonna wanna see on the output, if they apply, of course, is that this metric is interpretable by nature, right? So let me give you an example of how it works. We have our process for extracting rules, and now when we have text generated by a model, we can just compare it against those rules, okay? The nice thing about this is that we can have a linguist look at the rules and add them in the checklist, or remove rules from the checklist, as you know, these are automatically discovered from many languages. So that way we can keep updating LAMBRA to actually be correct, because currently we have only the automatic extraction rules for all languages except Greek, Russian, Italian, and Spanish. So basically what we do is, given an output, we're going to parse the text, and then we're going to see if our rules are, you know, adhered to. But now there's a little problem here, which is the fact that if you have potentially noisy text, right, or grammatically incorrect text, this actually throws off our parsers. So what we had to do is make our parsers robust to, noisy text that potentially has errors, right? So text like from L2 speakers like me, that whenever I speak German, which I haven't done in a while, but whenever I spoke German, I basically did a coin flip between whether my object should be in accusative or genitive or dative. Okay. So what we did is we used Unimorph to get examples of different inflections of the same lemma, and then given a tree bank, if we found a word that we also got a match on Unimorph, then we substituted it with a different inflection of the same lemma. So in this example, we took the Greek word ikismo that you see in Greek, which actually agrees with everything that it should agree with, and then we substituted it with its plural version, which now does not agree with the determiner and the adjective like it should. Okay, so we created noisy sentences where now the dependency links remain the same, but what changes is the morphological analysis of that word. Okay, and then we retrained our, I think it's stanza parsers on the clean data and the noisy data that we created. And now what we end up with, as you can imagine, is a more robust parser that can better parse noisy text. So let me just show you very briefly results. On dependency parsing, in this check tree bank, when we have clean text, the label attachment score is 89.7. But if we use the original parser that's only trained on clean data, and we test it on noisy text, then we have a drop in performance of 2 points, whereas our parser that has been retrained and is more robust, it actually has a smaller drop of just 1 point from parsing clean text. So, it's still not on par with parsing clean text, but it is better than, not doing anything. A similar story in producing the morphological analysis for each word. Clearly the model, because these models are multitask models, basically use information from syntax to predict morphological features and the opposite. So that's why basically what we're doing by training it on noisy examples is we make it rely less on morphology to predict the syntax, and the opposite, right? So I maybe generalized a little bit better, but the good thing is that in any case, it does a little better in parsing noisy text, which is what we care about. So now we have our good parsers, and what we did is we evaluated all of the data, all of the system outputs from machine translation systems from the WMT shared tasks. And then I'm just gonna show you a couple of examples. Before I go there, I do want to mention that Lambert does correlate well with human scores. It doesn't correlate as well as the state-of-the-art machine translation techniques like, Comet or whatever. But our metric is interpretable, okay? And obviously, our metric only cares about the well-formatedness of text. It doesn't care about whether the translation was actually accurate, okay? Ignore here the German line. I don't know what's happening with German. We had trouble with making things work. But for the other languages, we got really good correlations. In the paper, you'll see that Lambert also correlates well with perplexity, which makes sense. It's one of the standard metrics that we have for well-formatedness of text. But as I said, Lambert can provide fine-grained analysis and is interpretable. So looking at some examples from WMT outputs for English to Russian translation, we can actually do a diachronic analysis and look and basically see how MT systems have gotten better at producing well-formed text. So, in 2014, the best system was around 0.78 as a score in handling case agreement between conjuncted nouns, whereas in WMT 18, it's closer to 90%. When it comes to case assignment for objects, again, it got really good to the point that at WMT19, Lambert says, yeah, like 99, like the system basically was correct in its case assignment for the objects 99% of the time. Yeah, so you can do this basically for any little rule that you want to study and evaluate these systems against. There's also rules that seem to plateau. It's not clear at this point whether this is because that's a rule that has 10% exceptions, because as every rule has exceptions, right? Which here we're actually ignoring, or if it's just that the systems are not just getting better anymore. Yeah, I think that's all I have on Lambert. So yeah, a bunch of things in this work, but the nice thing is basically using the rules that I talked to you about and packaging them in a as a checklist that we can compare now automatic language generation output against. And Lambert is available online and so on. So I'll stop here before I go to the next section.
Okay, thank you. And questions, either raise your hand or just use microphone.
So the next,
I can probably start with a question. So how do you deal with syncretic forms?
With
like for instance, like in Russian, you have like accusative that could be syncretic with nominative or genitive, depending on the animacy.
Right. Well, you mean how to deal with it?
Well, how do you resolve it? Like when you have the raw text, so you need to tag it. So how do you keep you consider all the options, or like
no, I mean
most likely one?
How does the parser or the morphological analyzer decide it, right? Presumably.
Oh, okay, so you basically just rely on the parser.
Yes, yeah, and that's because of that reliance on the parser. That's why we try to make it better, like more robust. Now these parsers, like UDFI or Stanza, don't really use, for example, animacy features or anything like that. Maybe you can gauge that from context, right? Or maybe if you use an encoder that is BERT-like, maybe it has some dimension that maybe captures animacy. I don't know. We should look into it. So maybe that information is there somehow. I honestly don't know. But yeah, you're absolutely right. Like there's all these like little exceptions, obviously, that we would need to include. But that's the nice thing. We could formulate this as a rule, right? And we could add it in the checklist that Lambert uses for Russian, and then use it. So that's actually our next step. Like after, well, this is to be presented at the MNLP in 2 weeks, but after that, the reason we released it is we want to have a mechanism. At this time, it's going to be just GitHub issues for people to correct the automatically extracted rules or add to them so that it becomes better.
Okay, thank you. Any questions? And Nathan, you're raising your hand. Do you have a question?
Oh no, it was before.
So that was by accident. Sorry.
Yeah.
All right, so we're almost at 1 hour, and I have the other section.
I think there's Andre raising a hand.
Yeah.
Hi. I have a question about Lambert. I see that it's a metering metric to measure waveformness, and I'm wondering, like, if it also works on zero shoot settings, like when it is applied on a language which was not trained on it, like how have you done some experiment on that, or how does it perform? Thank you.
So yeah, so I honestly have not. So LaMDA relies on having a good parser for the language. And also the extraction of the rules relies on having a good parser or, a decent tree bank. So I don't think that it would work well unless, a zero-shot parser, unless that parser would do actually really good on that language because it has seen many related languages. So maybe it will work for Faroese, right? Because there are tree banks for Icelandic and Swedish and Norwegian and Danish and German and Dutch and all these other Germanic languages. So maybe it will be okay for Faroese, out of the box. But, using it, I don't know, for like Tagalog, where I don't think we've seen any other related languages to it, probably not. So yeah, we have to have a good parser. But hey, UD is expanding, so.
Okay, thank you.
Sure, you're welcome. All right, so I think I'm gonna go ahead. Is this supposed to be like just an hour? I mean, you can leave. I don't know. I have one more section to go through.
It can be a bit longer. That's fine.
Okay, I'll try to go quickly just because I think the next part is interesting. Yeah, so now there's another type of thing that we want to discover going beyond morphosyntax. And this has to do with semantic subdivisions. And I'll explain what I mean in a minute. So think about learning a new language. Presumably many of you have learned English, if it's not your native language, since you can follow along with this talk, presumably. Or, if you're English speakers, you are very interested in learning other languages and so on. So in fact, Duolingo says that, based on their statistics, there's many, many reasons why people learn a new language. A lot of them are related to work and school and travel and so on, or culture and family. So basically, it is crucial or important that we somehow develop content and tools to help learning a second language, right? L2. So at the same time, another motivation for this work is that there's ongoing efforts for the revitalization of endangered languages. As you may know, there are hundreds of languages that are endangered. For example, a UNESCO report in India identifies that a major reason for this is the primacy given to English and Hindi as the medium of instruction in schools, completely ignoring all the other local and native languages, except maybe for Tamil in Tamil Nadu. So communities themselves are taking initiatives to curate learning content. So at the same time, curating learning content by hand can be super expensive, and it takes a lot of time. It takes a well-versioned teacher and so on. So here we're asking if we could maybe automate some of the process of this type of learning content curation, okay? We look at a very, very small problem, which is the task of L2 vocabulary acquisition. So basically, we want to help someone learn words, given that they know a language, let's say English, and they want to learn a new language, let's say Spanish, okay? So now, when you want to learn mappings in this setting, there's some words that are easy, let's say, okay? There's a word like linguistics in English that has a very nice one-to-one mapping to linguística in Spanish, okay? Then there are some words like bank in English, which have a one-to-many mapping. So bank can be translated as banco or orilla in Spanish, exactly because bank actually has two very, very different senses. One refers to financial institution, one refers to a river edge, and Spanish uses different words for these two things, okay? So these two things are, let's say, easy to learn, right? Native English speakers understand, they have no problem with the first ones, and then the second one, you can inherently understand when you're referring to a financial institution and when you're referring to the river's edge. So you can learn that mapping just, by, studying. But then there's another type of mapping. So then there's words like wall, where inherently there's no different senses that you can map them to. But then when you go and look at Spanish, then you see that, okay, this could be translated as muro or as pared. So basically now we have distinct translations for what seems to be the same word sense in English, okay? So this last portion is exactly the focus of this work. So these fine-grained lexical distinctions arise because of languages carving up the semantic space differently, right? So the semantic space of wall is divided into fine-grained subspaces in Spanish, which English doesn't seem to care about, okay? So this is the thing that we're trying to help learners capture. So maybe I'll leave this slide up for 5 seconds, but maybe based on these images, you could have a guess on how the semantic space or wall is divided in Spanish, and I will give you the answer later. 1 second. Okay. So here's how we're going to do this. First, we need to find such examples. So what we do is we start with a parallel corpus between English and Spanish. We align it, and then we filter all of those alignments to extract those that seem interesting, right? That seem to have the property that I told you about. So we have these choices. So, you know, we have here, I'm showing you some examples. So there's wall in English that in Spanish could be muro or pared. There's the verb to rule, which in Spanish you could use either reinar or dominar or gobernar. Or you have ticket, which can be a multa or a boleto or an entrada, depending on something in Spanish, okay? We do one more step here where we try to find the ones that in English have different word senses that map very well with the words in Spanish. And because these fall into the second category of words that I told you about, which we assume that English speakers can easily learn by mapping them to the English word senses as opposed to the, you know, to the form. Yeah, because we are, again, interested in the more challenging scenario. That's definitely more interesting. So here's what we're going to do, very similar to what we did before. We are going to train a model to try to perform the task that we want the learners to do, and then we're going to extract human or machine readable rules from that model. So the model here is basically the following. We're going to have examples of the words that we want to select, a translation for, and then we're going to learn the model that will try to do exactly that. Select whether the translation, for example, for this instance of wall, given its context, should be muro or pared, right? This is very similar to word sense disambiguation models, except now our targets are not senses in a monolingual setting, but they are senses, they are the words in another language, the corresponding words, the corresponding senses in another language. And then from there, we're going to extract the rules. So how do we learn such a model? Okay, so for each word that we care about, we're going to have some training data that are basically parallel examples between English and Spanish, that there's all of these sentences will have that word that we care about. So in this example, we have an input that says, for weeks we have waited outside the walls of Paris for your arrival, and then that the translation of that sentence use the word muro. The translation of the second sentence use the word pared in Spanish. Okay, and this is actually our label. So now we have that model. How does that model look like? What we're going to do is we're going to take this sentence and extract lexicosemantic features from that sentence. Here's what that means. It means that first, we're going to take that input and we're going to find content words. In this case, it's just walked, city, foot. And then for each of these content words, we're going to add features that correspond to their lemmas, to their word sense, according to a word sense disambiguation model. And then we're also going to have bigrams between them. Here there's 3 content words. So we're going to have 3 bigrams. I'm not showing you the third column of rules. So we have walked, city, city, foot, walked food, and so on. Cool. So now we have these features, and these are the input to our model, and then the output is again, the choice between the options in Spanish. All right. So now we have learned this model over the training data, and we use again as a simple comparatively model, a linear SVM, which is very nicely interpretable. So here's what that means. It means that given each of those features, we can get different weights, and these weights will correspond to the different output labels. So this means that what you see here is like, if a sentence has hang and wall in English, in that sentence, then the model thinks the output will be pared. If the sentence has walk and city in that sentence, in the English side, the model thinks that the Spanish one will have muro and not pared. Okay. So maybe looking at these, you can again maybe guess what's the difference between muro and pared. I don't know, you can write in the chat, but I will give you the answer in a minute. But the answer is here, okay? Basically, the top images for muro are walls that are outside, like the city walls or a garden wall, and that's a muro. Whereas when you're referring walls from the inside, like the inside walls of a house, the ones where you hang stuff up, then you'd use pared, all right? Cool. So now we check how well our model is in actually choosing the correct translation at the word level. And we compare against a bunch of things. One is the frequency baseline, that blue line that is basically selecting the most frequent output always. And you can see that how that works. So that's basically our bottom line. Then there's another interpretable model, like a decision tree, that is better, but the linear SVM is much better. And then you have a BERT-based model, which performs better at selecting the output translation, but BERT is not interpretable. Okay, so among interpretable models, linear SVM is really nice and wins. But at the same time, it's worse than BERT, but we cannot show BERT weights to a human and expect that they learn something. Okay, so maybe in the future, at some point, we can apply interpretation methods to BERT. So let me show you real quick how we evaluate this and how this can be applicable in when humans actually learn. So what we did is we wanted to study if we can aid human learners in this vocabulary acquisition. So we created an interface that looks like this. What we took humans who didn't speak Spanish, okay, and we showed them this interface with some instructions that says, hey, here's this source sentence in English on the left, and there's the word that we care about, walls, okay, it's highlighted. Please choose, how do you think you should translate that word? Should it be muro or muros or muralla, or should it be pared or paredon? Okay, and they also select how confident they are in their predictions. Okay, so the moment they select those and then they click continue, they get feedback that tells them, yes, this is the correct prediction, or no, you made a mistake. And then we aggregate all the information to see how well we learn, right? Now, if this is our control setup, where it's exactly what I showed you before. And basically, if you take someone who doesn't speak Spanish and you give them this task, essentially they will start with chance accuracy, right? They won't know how to select between muro or pared for translating wall. So the assumption is that they're going to start with chance accuracy, but as they go through the examples and they get feedback on what answers are correct or not, then they may grasp patterns and then start improving. Okay, so this is our control setup. In the treatment setup, basically, we first show them the rules that our model learned. So we tell them, hey, our model said that if the source sentence contains phrases with climb wall or city wall or brick wall or jump wall, or if there's these words in the sentence like climb and man and high and within or Jericho, then it will probably be Muro. And then I'm not going to read the features for Pared. Okay, so they read these rules before they start the annotation, and then in the interface they can review the rules, and at the same time when they get feedback, then we also highlight which rules, if any of the ones we show, are actually applicable in this example sentence. So here, there was the word stone that was also in a list that our model thought was important. It's an important feature, so we highlighted. You see a little bit kind of like highlighted with yellow, right? So they have this extra feedback that we make it easy to them to see which rule applied to this source sentence. And then we just aggregate results. We do some proper statistical tests to make sure that our study accounts for the different pace of the learners and the different order that they saw the training examples on, and so on. So in our study, we focused on Spanish and Greek, and we had 7 learners with 9 words in Spanish, 9 learners, and 10 words in Greek. And there's a bunch of interesting things here. On the x-axis, I'm showing you how many examples they had to go through before they got 10 examples in the row correct for each sense. Okay, so when they did that, then they were like, okay, now you have learned the distinction, you can move on to the next word. Okay, so the first important thing is that even from the very, very beginning, you see with like 5 examples, the learners that show the rules in the beginning are already doing a lot better, especially in Greek. Okay, and again, these are people who like have never studied or learned anything in Greek. In fact, we had to transliterate most of the Greek words so that it was easier for the learners, as opposed to having them read stuff in the Greek alphabet. Okay. And at the same time, even so, you see how the learners improve. So in yellow, you see the control setup. So we can confirm that just by seeing examples and learning and seeing if their prediction was correct or not, humans do learn, right? So they get better, as you see in the yellow line. But with our rules, they get better faster, and they start at a better place. So yes, our rules result in increased learner accuracy, and they learn faster. Basically, they need to see much fewer examples. Cool. And then we do a little bit of analysis that I'm going to go very briefly through. So the quality of the rules, the quality of the model affects how good the rules are, and in response, that affects how fast the learners learn. But the very nice thing is that rules helped more for words on which the learners perform the worse. So, the harder a word it is to grasp the semantic subdivision, the better the gain. Okay. And these are words like wall and farmer and oil. Okay, which have quite fine-grained distinctions, at least in Spanish. Then we also ask how effective are the descriptions in aiding the learners. So obviously, the better the performance of the lexical model from which we extracted the rules, the more the rules helped, the more presenting those rules helped. For PIL, our model's accuracy is quite low. It's close to 60%, and there we had quite a few gain, for example. Okay, and yeah, so that's all I have here. I'm gonna stop for questions, and then I'm gonna end. I don't really have any other slide. I only have like one more slide, which I want to show you because it's my collaborators. Questions?
Okay, any questions?
Yeah.
Nathan?
Hey, so this is cool. Is there literature in second language acquisition and language pedagogy on this type teaching this type of lexical distinction? And is the main, because I know the question of should you give implicit or explicit feedback is well explored for things like grammar, right?
Mhm.
There are all these questions about what's the best way to give feedback regarding grammar. But I think, but maybe this sort of lexical semantic set of issues is underexplored.
Yeah, your second statement is correct. I am like 90% sure that it's very underexplored. And I am in contact with someone who studies L2 acquisition to try to figure that out. But we did a small search on, I don't think we did, I mean, none of the co-authors in this paper are experts in L2 acquisition. We did talk with people at Duolingo and another startup to gauge their reaction, and they said that this was really cool and they hadn't seen something that was like at least so specific. So yeah, that's all I have. If you do know something about L2 acquisition or someone, we should talk.
I do know some work on prepositions, so that's
Oh, right.
the other, that was going to be my next question, is like this is great for content words which have fairly clear distinctions. What about function words and grammatical things? Do you think there's a connection to be made there?
Yeah, these are going to be harder for sure. But yeah, I mean, we could look at it. We definitely only looked at content words like nouns and verbs mainly, but you're absolutely right. I mean, I still struggle with English prepositions. I was taught some general rules, but so yeah, this is definitely super interesting. So
yeah,
we are looking into this. This is also to be published at EMNLP in 2 weeks, to be presented at EMNLP in 2 weeks. So this is hopefully the first of many works going deeper into these types of things.
Just to add to that topic, I think I remember some work from Brian McQuinney, who did like preposition L2 learning. Like they had built some kind of
yeah, it was Ivy Wong who was a student
yes,
or worked with Brian McQuinney.
That's all I know of. Yeah,
I can send you, I can put the link in the chat.
Okay. Yeah, I think I took a note too.
So, and did you focus only on the mapping between like one sense in the source language to 2 senses, or there were more senses?
No, there were actually more. So there was an example in Greek that had like 5 options, because Greek. Well, I should say English, and it's syncretism, but anyway. Yeah, so yeah, it wasn't just 2. We also had examples with more than 2.
So when it's suppose like 4 or 5, how harder it is? How many more examples you need to show or produce? Or is it pretty much the same?
So no, it's actually, I don't know. I think we have in the paper, in an appendix, we have a breakdown by actual word. But basically we have this plot per word, but I don't remember now. For sure, the chance start for the no rule startup is much lower. So basically that yellow line starts much lower, but the red line also starts a little lower. But so it's kind of like they start much lower and then go high. But I can find that and get back to you, because yes, you're right. This is an interesting comparison to do.
Thank you.
Cool. And there's a message on the chat with a link to the paper that we were talking about. Yeah, so basically that's all I have. I want to give a huge shout out. Oh, well, I guess future steps. The code for this is also publicly available. So there's a bunch of things that I told you about, like extracting morphosyntactic rules and word order rules and stuff like that, and also going a little bit into semantics. What we are actively doing is applying this framework on more real low resource languages. So I'm working with linguists that are right now documenting POMAC, and we're trying to apply this framework. And David Mortensen, one of our co-authors, is working with Wong that we're trying to work on. So there's that. Another idea is to use multimodal features. So for example, show images, because these are also much easier for humans to extract patterns from. And I'm guessing you saw this when in the example that I showed you with the wall and pared and muro. The order is a little off, but there's this idea that maybe we could use similar techniques to also discover like cultural rules somehow. That's kind of like fuzzy, but this is something I've started thinking about. Like, can you look at parallel data and how they have been translated, and maybe uncover semantic divergences in the translations, which allows me to highlight the talk that Eleftheria Briacu is going to give, I think, next week at the NLP with Friends venue, that is exactly about that. So, maybe there's some common ideas there. But the other thing that I'm really excited about that I couldn't talk to you about because probably be submitted places, it's creating a visual interface to allow linguists and speakers to explore all of those rules, give feedback, look at examples, look at counter examples, because these are almost always the most interesting. And this is something I'm really excited about, and that we're right now working on. And with that, I want to say that basically all of this work was done with people at Carnegie Mellon, especially Aditi Chowdhury and Aditya Pratapa, and a bunch of other students in collaboration with David and Julia and Graham. I'm going to stop here. Thank you very much for sticking with me on a Friday evening or a Saturday morning. Just reach out if there's any interest, if there's anything that you want to collaborate on, or you have my email and my contacts. Thank you.
Yeah, thank you so much. Thank you so much. And yeah, the recording will be published shortly after the meeting. Yeah.
Cool. Thanks.
Thank you.
Thank you, Antonis.
Sure.